Hello, everyone. Uh, my name is Harshal. I work as a DevOps engineer at HelloFresh in Berlin, and I'll be speaking about our Kubernetes rollercoaster ride at HelloFresh. So, at HelloFresh, we have been running Kubernetes in production for almost a year and a half. And today's presentation is mainly about the kind of problems we faced initially during our implementation, some of the issues that brought us some downtime, the lessons we learned from it, and some upcoming challenges. So these are the three sections in which the presentation is divided. So let's begin. So first of all, a quick introduction to HelloFresh. Uh, HelloFresh is a meal kit subscription company, which means you go to our website, you subscribe to our plans, and then we show you a weekly menu of 15 different recipes. You can decide which ones you want for a particular week, and then we ship everything required to cook that recipe to your home. So that's the business model. Advantages of that business model are you get fresh ingredients with a very short supply chain, and you get to try out new recipes. So if you want to try some new dishes and stuff, it's a good way to try them out. A quick overview of how we used Kubernetes in HelloFresh. So right now, Kubernetes is running 95% of our services. We are completely driven by microservices, and almost 95% of our applications are running on our Kubernetes clusters. Our migration began almost 18 months ago, and we went from 0 to 95% in this time period. This helped us reduce the number of instances on our environments by 1/3. So we almost reduced 400 EC2 instances while the team size has doubled. So the impact is pretty big. So what are the advantages which we faced by migrating to Kubernetes? So the first advantage is autoscaling. So with Kubernetes, we have two layers of autoscaling, which means we can expand our clusters when we want more nodes, and then we can expand our applications as well. So the first layer of our autoscaling is for nodes, where if your cluster does not have enough resources, it expands automatically. And the second layer of autoscaling is at application level, where you are running X copies of an application, but they are not enough to sustain the load. You add X plus 5%, 10%, 20%, and so on. So a good example of this is one of our critical components is called API v2. So we generally run 18 copies of that microservices as a bare minimum. But because most of our workloads come during the US working hours, when people in the US are looking at menus and ordering things, when the US wakes up, we see the load is coming slowly piling up. So we scale based on the CPU utilization of that service. So we have set the ideal CPU utilization as 70%. As soon as the CPU utilization of that service goes beyond 70, we add more replicas. And as we add more replicas, the cluster doesn't have enough room for those replicas to run. So cluster also expands automatically. And then as US goes to sleep, we scale back, and we reduce back from 18 to 40 and 40 back to 18. And that happens on a daily basis. So our applications expand and contract, our clusters expand and contract without any problems. We don't waste a lot of money on extra or pre-warmed resources. We just scale up when we need to and then scale back down. And that has helped us a lot. The second point that comes with this is resource efficiency. So in Kubernetes, you can decide how much CPU and memory should be allocated to each and every pod. A lot of times people just go by empirical values. They'll just go by their gut instinct saying, I need half a core for my application of CPU and maybe 100 MB of RAM. Maybe that is enough, maybe that is not. So what we do is we keep running checks on our cluster. We keep on checking what is the peak utilization of a service in a 24-hour period. And then we compare that with what they have requested. So if you have requested 100 milli CPU and you are using probably just 25, then we ask you to reduce your allocation so we are more correct, and that helps us save money by reducing the requirements of a cluster, so we can pack more pods in a single node. There is also a dangerous downside to this when you request less and consume more. So for example, you have an application where you're requesting 100 milli CPU, but your application in reality is consuming, let's say, 800 milli CPU. So when such an application gets scheduled on a cluster, the Kubernetes scheduler will think, this application is requesting 100 milli CPU. I can probably put it on a machine where I have 4 cores, 3.5 is used, 100 more will not be a problem. Scheduler puts it there, and then the application consumes a lot more. It actually causes resource starvation for everyone else. So we take that much more seriously. So if you're using X amount, it's better to go X plus 25% more, but not under, because that results in a lot of scheduling problems, a lot of resource starvation. And the third thing, and the next thing that we get with our Kubernetes migration is declarative infrastructure. So before moving to Kubernetes, we had all our infrastructure as code, but we did not have CI/CD for it. So it was a very tribal knowledge kind of a thing where 2 people in the whole organization knew how to update something and run that update properly. But what we did here is added a CI/CD pipeline for our infrastructure as well. And that has helped us get a lot of PRs, and even the smallest changes, we could just do them right away without having to wait for someone else with specialized knowledge to run things correctly. So a quick look at our infrastructure. Like the overall view of our infrastructure is like this. All our stateful stuff sits on RDS on AWS or a self-hosted MongoDB. We are a completely AWS-driven company, so all our services are running on AWS. We have still some legacy applications that run on EC2, and those applications are exposed to everyone else via console. And then everything else runs on Kubernetes clusters. So you have dev, tool, staging, and live. So these are the 4 clusters that we manage. Now, if we look at internals of our Kubernetes clusters, all our clusters are managed by Amazon's EKS. So inside the control plane, we have chosen for core DNS to be our DNS solution. AWS VPC CNI, that's the networking plugin that is used for maintaining the internal cluster network. That's a default with EKS. But even before moving to EKS, when we were running our Kubernetes cluster with a tool called kops, we still had this networking plugin. Our worker nodes are EC2 instances, mostly M5, 2x large. For monitoring, we use Prometheus as a metrics mechanism. Nginx is our ingress solution, so all our ingress resources are served by a single Nginx controller. And then we have FluentD and Graylog for logging. So all our logs are captured by FluentD, sent to Graylog. And Graylog runs outside of the cluster. So when we started our move to Kubernetes, one of the first problem was developer tooling. How do we abstract away all the Kubernetes complexity from our team members and expose them only what they need? So to solve this problem, we went with Helm starter packs. So Helm starter packs are nothing but templated Helm charts with a lot where you can build in a lot of intelligence. You can add a lot of values and if then conditions and so on. And based on those value flags, you can keep on switching the behavior of a Helm chart. So let's look at one of the examples for this. So let's say in HelloFresh, one of our developers wants to expose a good Grafana dashboard. So any developer X, he goes to Grafana, creates a dashboard. He has all the panels he wants. Everything good is good. So he just has to simply export that dashboard as a JSON file, save it in his application chart directory under dashboards, and just write 2 lines in the values file. So all he has to do is this. Just write these two lines, and that brings this dashboard to Grafana persistently. Now, how does that happen? So the starter chart actually has some of the logic built in here where we loop over the values and we say if the value is enabled and if it is, and if you have a dashboard slash star present any file, then for every file we create this config map. And then with Grafana, we also run a Grafana sidecar container. Now this Grafana sidecar container looks for all config maps with this label. So as soon as it finds a config map with this label, it takes that config map, extracts the file, adds to Grafana's dashboard directory, and the dashboard is visible. So all of this complexity gets hidden, and for the developer, it's as simple as putting a file somewhere and enabling something via a flag. So the developer doesn't need to know all the config map complexity and the sidecar complexity or anything at all. So we have used similar features for a lot of other Kubernetes resources. So pod autoscalers have been implemented this way. If you want to expose metrics of your application, you can create service monitors in a similar fashion, and so on. So this has really helped us a lot because we have hidden away a lot of Kubernetes complexity from our teammates. Now, the problem number 2 that we had in our Kubernetes lifecycle was legacy communication. So we did not move to Kubernetes all in once. We moved service by service. We moved a few microservices, made sure they are looking okay, then we moved a few more. That means there was always a time when we had old and new running together, and we had to ensure that the communication is still seamless. So in order to do that, let's take a look at what our infrastructure looked like. So this is what we had. We had legacy applications, LA, LB, and LC exposed via console. And then you had a Kubernetes cluster where you had some applications running. Now, how do they talk to each other? So first thing that we got was from console, they have an application called console agent, which can run within Kubernetes. And then it can expose everything that console is exposing to my Kubernetes applications. So what we did, we created a cron job, which will talk to the console agent, understand what are the endpoints, and then create internal services. So my application can now talk to LA, LB, LC as local services. And this was fine. This worked okay because this cron job was running every 5 minutes. The problem was if something changes here between those 5-minute windows, that change is not instantaneous. So some endpoint changes, it takes almost maximum of 5 minutes for it to reflect. But an even more dangerous trend was cron jobs in Kubernetes can stop running if an older schedule has failed. So if one instance of the cron job failed, it stopped running, it would not update anything anymore, and suddenly we are looking at old copies of the endpoints, and our communication would just go crazy. So we had to be very alert and in monitoring the cron job and making sure everything runs all the time. So this was not a suitable solution. So we had to re-engineer a little bit, and it was 4 or 5 months ago that we also moved from Kube DNS to Core DNS as our DNS solution. So what we did, Core DNS also has an extra facility called DNS forwarding. So we decided that for all our legacy applications, we will have a suffix called .service.console. We chose that suffix, and then we went to Core DNS and said, if you find anything with .service.console, you can straight away pass it on to console agent, and console agent then moves it to console and then resolves it further. So this made our solution instantaneous. Every request now going from our Kubernetes applications, instead of referring to a legacy service as LA, it would become la.service.console. And then it goes to Core DNS. Core DNS understands that's a .service.console, so sends to console agent, which sends it to console and then gets resolved. So all of this was instantaneous, no cron jobs involved, one-time configuration, and everything fixed. So this helped us in a much better way with legacy communication. Now we don't use much of it because we have only 2 services running on legacy, but still this is a this was a good way to solve a problem which we had initially. So now let's look at the next problem. The third problem was secrets management. So how do we manage secrets? So till almost 3 months ago, we had a very bad solution for managing secrets. So what we had was a shared private key, which was known to everyone, and everybody would use that private key to encrypt their files and upload them on GitHub. And then we had a CI solution that would also have that shared private key and use it to decrypt all our secrets and use it further. So this was definitely not a good way of going about things. So we decided to use HashiCorp Vault as our solution. So what we did then was Vault was running in our tools cluster, and every Kubernetes cluster that we have had a small internal application called Vault Mutator webhook. What this small application would do is it would look for all the workload objects, whether it is a deployment, a stateful set, a cron job, anything. It would look at those applications for a particular annotation. So it would look at an annotation called vault injected. So vault injected was the key, and the value was which path in vault would you look for a secret. So the moment this mutator webhook sees any workload object with this annotation, it would go to vault, go to this path, and then take everything and create a Kubernetes secret inside, and then mount that secret into the pod of that parent object. So the moment you have a deployment with this annotation, you get a secret created from Vault, and then that secret is mounted within the pod. So the mutator actually modified the pod spec before the pod gets created and exposed everything. And that helped us a lot because now our GitHub repositories are clean. There is no encrypted files or anything. Because earlier, one of the problems was that if someone forgets to encrypt the file and uploads it to GitHub, all your secrets are there. So with this, there is no need to do anything. Everything is sitting in Vault, and from there we just pull whatever we want. So now the next section is about throwbacks. This is about some of the issues that caused us downtime. So the first one is memory leaks from Tiller. So this problem happened almost from Helm 2.8 till 2.12. So Tiller is the server-side component of Helm, and Tiller is the entity which is responsible for running everything you want on the Kubernetes cluster. Tiller is the one who is talking to API server and getting things done, right? So there was a memory leak in Tiller which was causing Tiller to take up a lot of memory, and that would really kill anything else that was running on the node. So we had to solve this problem by moving Tiller to a separate instance group. So we created a new set of nodes where only Tiller would run and nothing else. And then we would have a cron job which would keep on rebooting kubelet on those nodes and keep on fixing this issue intermittently. So with that, we were able to survive for some time, but when the core solution arrived, we were okay. But this problem caused us a downtime a few times where people were not able to deploy just because Tiller was down. The second issue that we faced and that caused us downtime was rolling update with kops. So before moving to EKS, we used to manage our cluster using a tool called kops. Now, with most of the Kubernetes solutions, what happens is, because the infrastructure is declarative, you make some changes into a spec, but that becomes active only when you recycle your old instances. So if I make a code config change now, it is not visible to the cluster directly. You have to delete the old nodes, the new ones come up with a fresh config. So when we do that with kops, one of the problems was that kops would not do a health check on the nodes. So the way kops rolling updates work is, when you trigger a rolling update, kops will go to a node in your cluster. It will remove everything from the node and then kill it. And then your cloud will spin up a new instance of the node with the new configuration, and that is supposed to join the cluster. But in our case, what happened was when we ran the rolling update, it took out one of our masters. And then when AWS spun up the replacement master with new configuration, cops assumed that everything is good and went ahead. Whereas what had happened eventually was the new master which had come up never mounted its EBS volumes. And because it never mounted its disk, we did not have etcd. And because cops proceeded further with the next master, it deleted the second master, and now I have lost etcd quorum completely, which means I cannot do any querying to my Kubernetes cluster. I cannot do any kubectl commands. I cannot do anything. And that was something which resulted into some downtime for us where nobody could talk to our clusters. Luckily, with Kubernetes, your applications are not affected by this level of outage. So our website was running fine, but nobody could do any deployments. Nobody could check anything. So this was an issue that we raised, and the community fixed it in like 2 or 3 weeks. But yeah, this was a good lessons learned. And this was one of the more complex problems that we came across recently. So when we were running with kops, our worker nodes were a combination of Ubuntu 16 and Docker 1703 installed on them. And what would happen is every day almost at any random time on some of our nodes, Docker would freeze, which means when you do a kubectl delete pod or when you do an upgrade and some pods are supposed to be deleted, kubelet talks to Docker, says, Docker, please delete this container for me. Docker goes ahead, deletes that container, but never updates itself. And because Docker never updated itself, kubelet always thinks that the container is still alive. So kubelet reports back to the control plane saying the pod is still in terminating state. And that would create a lot of mess. Our updates would never work correctly. And this was a big problem because it was very uncertain. And when we checked for this issue, the only solution we found was to upgrade to Docker 18. Now, we were okay for upgrading to Docker 18, but the tool that we were using for our cluster management did not allow Docker 18 with Ubuntu 16. So the next level of dependency was that we had to update our OS from Ubuntu 16 to Ubuntu 18. We said, okay, let's go. We'll take Ubuntu 18 with Docker 18 and move on. The moment we did that, our core DNS stopped working. So what happens with Ubuntu 18 is it handles etcd/etc/resolve.conf, the resolver, in a very different manner. It has its own service, its own protections for resolve.conf, and it kind of points you to somewhere else, and that causes core DNS to fail. So we had to actually write a user data script that disables the protection service, copies etcresolve.conf from somewhere, make DNS point to the right AWS gateway, and then move on. So it was like a multiple layer dependency that we had to keep on fixing to solve this problem. So this was one of the tougher issues that we had to go with. But besides that, we did not have more of complex issues in our Kubernetes migration. So the next section is about upcoming challenges, the challenges that we have and the challenges that we are working on right now. So the first challenge is tribe namespaces. So in today's keynote, we already saw the Conway's law, where architecture influences the organization and organization influences the architecture. So it is kind of relevant for us as well. In HelloFresh, our organization is divided into multiple tribes, and tribes are further divided into squads. But this does not reflect the way our code is laid out on our Kubernetes clusters. If we look at our Kubernetes clusters, everything is running on a single namespace called default. And that has quite a lot of disadvantages. Because everything is running on default, because everything has a single ingress controller, everything just passes through one single load balancer. Everything is governed by a single Nginx configuration on the ingress controller. That means any one of our team members, if that person pushes a wrong configuration via wrong annotations, it can mess up the Nginx config. It will break everything for everyone. Another complexity that can happen with this kind of a structure is our Prometheus becomes too big. We have one Prometheus instance which looks at a single namespace, and that is not good enough. So we had to come up with a solution for this, and that was tribe-specific namespaces, which means every tribe gets their own namespace, gets their own ingress controller and load balancer, gets their own Prometheus. So everything is sharded vertically according to tribes. And then everything has a much lower cardinality than what we have in our default structure. This also helps us set resource quotas. So we can also define at namespace level saying, you are a small tribe, your application is not complex, you can use 50 CPU and 200 GB memory, whereas a bigger tribe can go for like 100 CPU and, I don't know, 500 GB of memory or something. So all those controls come into picture when you go with tribe level namespaces. Another thing that helped us with the EKS migration is role-based access control of our clusters. So now each and every person in our team has his LDAP credentials, his login credentials associated with the roles on the cluster. And with tribe-specific namespaces, we can also fine-grain this control. We can say person of tribe X has admin privileges on his tribe, but everywhere else he can only have read-only access. And that is something which was not possible with a single default namespace-based allocation. So this was the first challenge. The next challenge is Prometheus. So the story about Prometheus is that Prometheus stole fire from gods, gave it to humans, but then he was punished for it. He was tied to a stone and he was cursed with a thing where an eagle would come, eat his liver every day, and the liver would grow back, so he would feel the same pain every day. And that is something that had happened with us also when we started working with Prometheus. Some of it was our own bad design, some of our mistakes, and then there were also some product level problems that we ran into. So the problems with Prometheus that we had were scaling and retention. When we started with Prometheus, we went with the default retention of 15 days, and we had very less services sending metrics, so it was okay. But then as we started growing and as we started using Prometheus actively, we actually ran into problems where we had much longer retention and every query would take up a lot of memory. And even humongous instances on AWS were not able to handle the workloads because just the sheer cardinality of each and every time series was too high. So now we are beginning with the vertical sharding of our Prometheuses, and also we are using a solution called Thanos. So if you've heard of it, Thanos is a long-term storage solution for Prometheus, which allows you to store your metrics on S3 or a object storage bucket, and then you can pull metrics as you need. And then they also have another component called Compactor, which can reduce your old data into a lower resolution. So by default, Prometheus will scrape data every 30 seconds, but you can say, I want raw data or 30-second scrape data for 2 days, and then 5-minute resolution data for 2 weeks, and 1-hour resolution data of 2 months. So that kind of keeps your cardinality in check, and that really helped us a lot. And the last challenge that we are looking forward to is Istio. So Istio is a service mesh. We tried earlier with Istio 1.0, and when we moved one of our services completely to production, we actually saw a few deficiencies. So there were performance problems. A lot of Istio sidecars were not getting the updated configuration fast enough. So we had very unpredictable behaviors and so on. But with Istio 1.1, we are seeing some better performance already. And we are also trying to see if our services work better with this iteration. And this is something that we are looking forward to. So yeah, that's it for today. And if you have any questions, please feel free.